Is the voice and the picture are they clear? The voice and the picture? Are the voice and picture clear? Perfect. All right. So today, inshallah, we will continue our topic, which is the chapter 8 topics, which are all right. Some of the topic we're going to continue, which are the addition reactions of alkene. The last reaction, what we have discussed the last time, it was addition of halogens to the alkene. So whenever we have alkene, when we allow it to react with, for example, bromine in the presence of CCl4, what we're gonna get, we are going to get addition reaction of the bromine. The most important thing about the stereochemistry of this reaction, we said this reaction is anti-addition manner, and therefore this is anti-addition, and therefore the products actually, if there is a stereochemistry, if this will be above the plane, this must be below the plane. So that's what we have said before. And the mechanism of this reaction, we said, first of all, we're gonna get, there will be a formation of a bromonium cation, where we have this type of intermediate. So we're gonna get this bromonium cation. Now, the other nucleophile will add from the other phase. So, regardless of the nucleophile here. Now, the nucleophile in this reaction, we have the bromine, so the bromine can attack the back side or the opposite side, and therefore we're going to get, at the end of the day, we are going to get the two bromine atoms are added anti-fashion, this case. Now, what if we have, inside the reaction, we have another nucleophile, such as, for example, H2O. If we have H2O inside the reaction, instead of the solvent to be CCl4, if we choose in the solvent to be H2O, in this case, the nucleophile here, which is the oxygen or the lone pair at the oxygen here, that's actually the one which will add similarly. And therefore, what we are going to get, now addition of a halogen and OH in this case. And that's actually what we call it. Whenever we have a compound containing two functional groups, halogen and OH hydroxyl group, then we call this halohydrin. Halo coming from the halogen and hydrogen coming from the OH. Do you follow me? That's actually like another reaction but similar mechanism. Another reaction to the alkene, another addition reaction to the alkene, but almost same mechanism. The first step will be the formation of the bromonium cation. The second step will be the opening up of the bromonium cation to form what we call it the halohydrin. Again, similarly, the stereochemistry of this reaction must be again anti-addition fashion, similar to the addition of the bromine. Is that clear? Is there any question about the halohydrin formation? Any question about halohydrin formation? All right. So the other reaction, or the next reaction, what we are going to discuss here, now again here the halohydrin reaction, as you can see, the halohydrin reaction, whenever we have, for example, if we take cyclohexene If you allow cyclohexene to react with Cl2 in presence of H2O, let me just assign this here. We have CH3 here. So for example, we have 1-methyl cyclohexene. We allowed 1-methyl cyclohexene to react with chlorine in presence of water now instead of CCl4. What we are going to get, addition of 2 parts of these 2 reagents. One is the halogen, which is the chlor, the other one is the OH. In this case here, the first adding part, which is the chlorine, it will be the electrophile. Therefore, this reaction will follow Markovnikov addition reaction. So it is again, halohydrin reaction is anti, and at the same time it is Markovnikov's addition reaction. So in this case, the chlorine, the electrophilic part, will add itself to the carbon which contains more number of hydrogens. As you can see, this carbon is connected to 1 hydrogen, while this carbon is connected to 0 hydrogen. Therefore, the chlorine will attack in here and the OH will be there. So what we are going to get, the chlorine is in this carbon, and if we make this is above the plane, for example, so below the plane must be the OH, and above the plane must be the CH3. So this is definitely extremely important example to understand the 2 aspects of this halohydrin formation reaction. First aspect, it is Markovnikov addition reaction. Second aspect, it is in this case, it is stereochemistry. The stereochemistry of this, it will be anti-addition reaction. So we have, at the end of the day, we have halogen atom and OH will add themselves to the carbon double bond carbon. They must add themselves in opposite phases. So one will be above the plane, the other one must be in below the plane, for example. They cannot be in the same plane. That's extremely important aspect of the halohydrin reaction or formation. Any question about it? Is there any question so far about the halohydrin reaction? Is there any question? All right, I will assume that there is no question, and therefore I will just go ahead. If you have any question, please stop me by opening up the mic at any time. Now, sometimes we may, instead of use a halogen, we may use another equivalent reagent, which is in this case what we call it NBS. And the NBS here, the similar thing with H2O, we are going to get here, this will be Br, and this will be OH, and this will be methyl. So the NBS is an equivalent of the bromine. So the NBS, it's simply, this is the reagent, what we call it, the N-bromosuccinimide. This case here, not the filament. So this is called N-bromosuccinimide. N-bromosuccinimide, as you can see it in your slide. So instead of adding bromine, in other words, we may add NBS. So whenever you see NBS, it means we are talking about bromine. So bromine in the presence of water, there will be addition or reaction according to Markovnikov addition, where the bromine will attach itself to the carbon with more number of hydrogens, and at the same time, the addition reaction regarding the stereochemistry, it must be anti-fission, where the 2 adding parts must add themselves to the carbon double bond carbon in anti-fission. Do you follow me? All right. Let's. Yes, please.
في الكلاس الماضي قلنا مثلا إذا ضفنا أسيد HCl الاتش تروح عند اللي أكثر هيدروجين والCl تروح عند اللي أكثر كربون.
Yes, that's the addition of hydrogen halide. Okay.
زين الحين هنا ليش صار العكس إنه الBr تروح عند اللي أكثر hydrogen?
Good question. Because in the HCl or HBr, for example, the electrophilic part was the H+, isn't it? Isn't that true?
Yes.
Now, in this case here, when we add bromine and the water, the bromine in this case, the Br is the electrophilic part. As I have explained in the previous slide, the bromine will form the carbocation. Do you follow me? It will form the intermediate which is similar to the carbocation. That's why actually in this reaction we consider the bromine or the halogen as the electrophilic part, and of course the oxygen here is always the nucleophile in this case. Do you follow me? That's actually why, according to this reaction, the halogen always we will consider it as the electrophilic part, and it will add itself to the carbon which contains more number of hydrogens according to Markovnikov addition reaction. Is that clear?
لكن إذا جينا نشوف الإلكترونيجاتيفيتي بيكون Cl هو الماينس.
لا طبعا يعني for example, which one is more electronegative, oxygen or chlor? Here, chlor or brom, which one is more electronegative? Which atom is more electronegative?
Cl.
لا طبعا. Oxygen is more electronegative. The most electronegative atom is oxygen, then chlor, then brom. You can check the numbers in your table. You will find it like so. Anyway, by all means, for the halohydrogen reaction, the halogen is the electrophile because it will form what we call it the uranium carbocation, and then the oxygen, it will be the nucleophile in this case, and therefore we should always remember to connect the halogen to the carbon with more, or which contains more number of hydrogens according to Markovnikov. And also we must always remember the stereochemistry of this reaction, in which the two adding parts, which we have here, the halogen and the OH, they must be in anti-addition fashion. Clear?
Yes, sir.
Sure. So, for example here, if the example in your slides here, in the slides, what would be the reaction or what would be the product and the stereochemistry of the product if you are adding, let's say, suppose this reaction. I'm just going to change it a little bit. Here, again here, for example, CH2, CH3, and then you are allowing this to react with NBS in presence of water. In this case here, as you can see, we should remember that this is halohydrogen formation. This is equivalent to bromine. This is equivalent to OH, which they will add. This reaction is Markovnikov addition reaction. So the halogen here, which is the bromine, should add itself to this carbon because this carbon contains more number of hydrogens, while the OH should add itself to this carbon. This is first. Second, these two parts, which will add themselves to these two carbons, they must add themselves in anti-addition fashion. So in this case, it must be your answer like this. So if we assume, for example, the bromine added itself from the lower side, that means the OH must be from the upper side, and the carbon, and definitely in this case, must be here CH2, CH3. So that should be or must be the product or the stereochemistry of the product which we will have for the halohydrin formation. All right, let's move to another reaction in this case, which is, we call it the hydration reaction. Hydration reaction. The next reaction will be hydration reaction or addition reaction. From its name, the meaning of hydration, it's addition of what? Hydration. It's addition of water, H2O. Now the H2O, it's like two parts. Now, for example, if you can imagine H2O, it's like we are adding this part and we are adding this part. So for the hydration of the water, if we are talking about the conventional way, most likely if you are going to use this as the reagent for the hydration, then the electrophilic part must be the hydrogen, while the nucleophilic part will be the OH. So therefore, this reaction will follow Markovnikov reaction, will be Markovnikov addition reaction manner. For example, if we allow any alkene to react with H2O in presence of, as a catalyst, in presence of strong acids such as sulfuric acid, for example, what we are going to get, hydrogen, addition of hydrogen and OH. I'm just going to use another color just to make it more clear what are the adding molecules in this case, or what are the adding parts in this case. So as you can see here, we have two parts. We are adding here, or we will add hydrogen and OH in this case. In other words, we are converting alkene into what? Alcohol functionality. So by this reaction, we are preparing alcohol. So whenever you study the alcohol synthesis, it will be one method for the synthesis of alcohol. It will be simply the hydration of alkenes. Do you follow me? So similarly here, so this is a reaction going to alcohol, or simply it is a method for the synthesis of alcohol reaction. So what we said here, the hydrogen here, which is the electrophilic part, should add itself to the carbon with more number of hydrogens. For example, some of you keep adding themselves or keep entering late. So next time I'm not going to allow anyone coming late, because that will interrupt the lecture. So again here, some of you asking my permission to enter the lecture late, which is, it simply interrupt the lecture. Please be on time and stay in the lecture in order not to interrupt the lecture in general. So anyway, if we have this alkene and we allow this to react with H2O in presence of H3PO4, what we're gonna get, what we should expect, that the hydrogen should add itself to this carbon, because this carbon is connected to 2 hydrogens, while this carbon is connected to 0 hydrogens. So what we are going to get, this is the compound, or this is the product what we are going to get. This is the alcohol what we are going to get. Do you follow me? What's the mechanism of this reaction? How this product has been formed? This is again always the same case. First step will be the formation of the carbocation or the carbocation equivalent. Then the second step will be the addition of the nucleophile to this carbocation. So in this case here, in the presence of H+, this is similar mechanism to the mechanism of addition reaction of hydrogen halide. So whenever we have carbon double carbon, you follow me, and then we allow it to react with H+. First step, the H+ here, or the double bond here, will be used to make a bond with the H+. So what we are going to get, a carbocation formation. The second step will be addition of or attack of the lone pairs in the oxygen as a nucleophile. What we are going to get then, what we are going to get CC, then OH2 plus, and then finally the oxygen will lose H plus to get back to the neutral product again, OH and then hydrogen. So that will be the mechanism of the reaction. In most of the cases, whenever we are talking about Markovitch addition reaction, it will be the formation of carbocation. So the electrophilic part will add itself first to the carbon with one number of hydrogens, then the nucleophile will attack. If it is a neutral, there will be a carbocation in it, then there will be a cation in it, there will be a positive charge in it, then finally losing H plus, we are going to get the final product. Do you follow me? Now sometimes we may use, instead of using H2O and H3PO4, we may use another reagent which we call it oxymercuration and demercuration. So, but before moving to that, is there any questions so far? Let's agree on something in order just to use the time more efficiently. Please, if you have any question right away, stop me by opening up the mic, because that's actually the most optimum way to use the time more efficient way. Do you follow me? So if there is any question, please stop me. All right. Now, as I said, for this reaction, so this reaction here, as you can see, it is Markovitch addition reaction. The hydration reaction of alkene must follow Markovitch rule. So I will write it always like this. It's Markovitch rule. So similarly, we may use the same, we may get the same product if we allow the alkene to react with first mercuric acetate in presence of H plus, and then finally, or let's say first step, and second step will be the sodium borohydride. It's like a reduction of the mercury, and then we are going to get again similarly OH and hydrogen. So again, this reaction is Markovitch addition reaction. So to make the story short, we may prepare or we may convert alkene to alcohol either by directly reacting them with water in the presence of H plus, or by first allowing it to react with this mercuric compound, what we call it mercuric acetate, then getting rid of the mercury by simply the sodium borohydride. So according to your procedure, in presence of water here must be, so this is mercury in the presence of the water. I will explain actually the mechanism of this reaction. So when we allow the alkene first to react with mercuric oxide in the presence of water, the first step will be simply this following this reaction or formation of a mercuric product here, OH. This is here called hydroxymercuration. This reaction called hydroxymercuration. Do you follow me? And why we call our oxymercuration? Oxymercuration means we have made an addition reaction in which, or it includes addition of mercury as an atom and OH as the other part. So it is oxymercuration. Then finally, in order to get the product, finally then we convert the mercury, or we reduce the mercury by using reducing agent, which we are going to be introducing later on. by sodium borohydride, so we are going to get OH here, and then finally the hydrogen. So this is simply the mechanism for the hydroxy, for the oxymercuration, and then finally demercuration, as you can see here. So this step, first step, we call it oxymercuration, and the second step we call it demercuration. Now the D, it's simply omitting or cancelling or deleting the mercury. So the first step will be addition of the mercury and the OH. The second step will be removing the mercury from the compound. Do you follow me? Now the question is why? Why we simply bother ourselves to make like two procedures for the synthesis of the same product? Do you see it? So as you can see here, we have like two reagents giving us exactly the same product, which is the alcohol in both reactions. If you use H plus or H2O in presence of H plus, or if you use this method, which is the longer method, what we call it, the oxymercuration, demercuration, we are going to get the same product following Markovitch rule. So then why we need, or we want, or we prefer the second method rather than the first method? Actually, always the second method is more preferred whenever we want to do hydration reaction or addition of water to the alkene. Is there any suggestion why the second method is better, or why we need another two methods for this synthesis?
Maybe it takes less energy.
No, actually it's more practical issue. Just keep it in mind. You know, these reactions, addition reactions, always they involve what? What did we say? That in general, the mechanism of these reactions, addition reactions of alkenes, they involve what? The first step always will be the formation of what? Huh? I know, but I mean, based on the mechanism of the reaction, always the first step will be the formation of carbocation. Exactly, Hajar, carbocation. So what we know about the carbocation, it is very reactive intermediate. It is, it's not stable species. Do you follow me? So the carbocation, since this reaction involves the formation of the carbocation, sometimes the carbocation is not stable, so therefore it may accompanied with what we call it rearrangement of the structure or the carbocation. Do you follow me? Yeah, in other words, sometimes it is not a secret. For example, I'll just give you an example for this, and please work it out at home. Just think about it at home. I'm not going to spend a lot of time on it. Now, for example, if you have this CH3 or CH2, that one CH, then C, CH3, CH3, then CH3, and then you allow this to react with H plus, in this case H plus with water. What should we expect to have? So if we use the first step, let me just delete this. What you are going to get if you allow this alkene to react with H plus in the presence of water, in this case we should expect to have a hydration product, right? اللي هو alcohol in this case. بمعنى hydrogen will add to one of the carbons. Where the hydrogen should add, should simply based on what should we expect here. This hydrogen should add to this carbon, which is connected to more number of hydrogens, and the OH will be there. We are expecting to have CH3, CH, OH, then C, CH3, CH3, CH3. This is what we expect to have, isn't it? Right? Unfortunately, we will never get this. This will be either minor or it will not form at all. What we are going to get we are going to get actually as a major product CH3, then CH3CH, then CH3OH. This is most likely will be the major product. Do you follow me? That's most likely to be the major product. As you can see, it's totally different than the previous one. What you can see here, what you will notice that there has been what happened in this reaction actually, what we call it rearrangement. In other words, the carbon chain was certain bottom, it has been changed to totally different carbon chain. That's actually what we call it, the carbocation. Now, what I want you to do, and consider this as part of your assignment, which you have to submit it on, this is the assignment of the stereochemistry, which you have to submit it by Wednesday. Add this reaction and this explanation, and explain that why this is the major product of the reaction. Add it to the assignment, please. All right? So consider it as a homework and add it to the assignment. Think. The point is to explain the formation of this product rather than that product, rather than the expected product. And of course, how you can explain it, the best option always is simply to write the mechanism of the reaction. Is that clear, guys? Now, anyway, that's actually the reason, because these reactions, generally speaking, whenever we want to make hydration, if we use these reagents, which is the H plus and H2O, most likely we are going to get rearrangement product. While if you use, for example, the other reagent, which is the oxymercuration demercuration, which is simply the HGO acetal in presence of H2O first, second sodium borohydride, we are going to get exactly what we are expecting, which is in this case CH3, CH, OH, then CH3, CH3, and then CH3. So that's for sure what we are going to get when we use the other method, which is the oxymercuration demercuration. That's why, as a recommendation, it is always recommended to use oxymercuration demercuration as a method for the hydration reaction. Do you follow me? Is there any question so far? Is there any question?
دكتور كيف كمان؟
ايش هو؟ ايش سؤالك؟ What's your question?
يعني كيف مرة رجعنا هذا قلت غلط؟
This is actually what I want you to do. Just think about it at home. See, just look here for that reaction. Just look for the mechanism and simply think. Just write the mechanism and write the carbocation which you are going to get, and think what's happened in order to get that product. I want you to think. I want you to make your work and make some efforts at home in order to find an answer. As I said, whenever we use if we use the hydration reagents as the H plus and H2O, most likely we are going to get some sort of what we call it rearrangement, which is simply another product than expected. While if we use the oxymercuration demercuration, we are going to get always the hydration product which we are expecting. After you finish this homework, after you try it and you solve it at home, then next week I will tell you what's the answer of this, or I may simply post the answer on the Moodle, so don't worry about it. But I want you to think about it. All right? So think about it, about the stability of the carbocation, so the driving force is always, so simply I'm giving you the solution, the key for the solution. The key of the solution is simply the stability of the carbocation. All right, so let's move to the third reaction in this lecture, which is simply another hydration reaction, but anti-Markovnikov hydration or addition reaction. So the third reaction which we are going to discuss in this lecture, which is simply, the third reaction is hydration reaction. Another hydration reaction, but it is anti-Markovnikov rule. Remember this. So the previous reaction we have discussed a hydration reaction following Markovnikov rule, in which the hydrogen always adds itself to the carbon with more number of hydrogens. In here, we are going to get, again, similarly hydration. In other words, we are going to add hydrogen and OH at the end of the day. But the selectivity is extremely important. The hydrogen will add itself to the carbon with less number of hydrogens compared to the previous reaction. So, let's just give an example for this. Let's say if we have CH3, CH double bond, CH, or simply CH3, CH3. And we allow this to react first with BH3 in presence of THF, which is a solvent in this case, and second with H2O2 in presence of OH minus. What we are going to get here in this case CH3, CH, C, CH3, CH3. I'm going to use this color here. Here we are going to get the OH, and here we are going to get the hydrogen. Do you follow me? While if you use the previous reagent, which was the oxymercuration demercuration, so the first step was HGO acetyl by 2. You just write it in here. First, second, sodium borohydride. But you are going to get CH3, CH, C, CH3, CH3. What did we say about the stereochemistry of this reaction? Is that clear? Fatma, is this clear? Perfect. Now, what did we say about this addition reaction? What did we say just a few minutes ago? We said this reaction is a hydration reaction following Markovnikov rule. In this case here, always Markovnikov rule, the electrophilic part, which is in this case the H will add itself to the carbon with more number of hydrogens. So in this case, definitely then, this will be, here is the hydrogen and here is the OH. Do you follow me? Now we are going to study, or we are going to introduce a new type of reaction. These reagents will lead to hydration. Again, it is a hydration reaction. Do you follow me? So at the end of the day, we are all going to add H and OH. But regarding the stereochemistry, it's opposite to Markovnikov rule. Here we have the hydrogen add itself to the carbon with more number of hydrogens, while in here, hydrogen will add itself to the carbon with less number of hydrogens. Do you follow me? Before explaining the mechanism and the details and why it gave us such type of selectivity, but I just want you to think of these two reactions and think of the difference between both. So the first this reaction we are talking about anti-Markovnikov addition manner, while the previous reaction we said this is hydration following Markovnikov rule. Do you follow me? So how and why simply this reaction proceeded like that? But before that, let me just specify also some other issue regarding the stereochemistry, that these two here, the hydrogen and the OH, beside they are Markovnikov, the stereochemistry of the addition will be cis or syn addition reaction. So it's again syn addition reaction. So we'll explain everything when we talk now, when we simply explain the mechanism of the reaction. So let's talk about the mechanism of the reaction in order to explain the differences of this hydration reaction from the previous one. The first step actually, as you can see, for this reaction, which is the addition of what we call it hydroboration. The first step will be hydroboration. So let's talk about hydroboration. So what's the meaning of hydroboration? From its name, hydroboration, hydroboroation. Hydroboroation, whenever you say ation, at the end of the day, it means addition. So it is simply the first step will be addition of what? Addition of what? Hydrogen and boron, because it's hydroboration reaction. So in this case here, what we have to guess now. So the boron and the hydrogen bond. This bond is polar, isn't it? It is the difference. It is the polarity of this bond. Which atom here will be electronegative and which atom will be electropositive? Or which atom will carry a partial positive? Which one will carry a partial negative? And why, of course? Hurry up, please. Which one is more positive or more positive in this case, the hydrogen or the boron? Why, Fatima, the hydrogen? The hydrogen is more positive? It's all about what? Electronegativity, remember? Yeah, of course. I know, of course. It's fine. But it's exactly now regarding the electronegativity. Remember that the boron, it's like metal. So definitely, what's the one important characteristics of the metal? It's their ability to lose electrons. So they have better ability to lose electrons than hydrogens. Always, if you check the periodic table, you will find the boron has less electronegativity, more electronegative. I'm sorry. The boron has less electronegativity compared to the hydrogen. So that's why actually simply the electronegativity will be partial positive and then partial negative in this case. Do you follow me? And that's, by the way, that's always the case whenever the hydrogen is attached to any metal. Either if this metal is boron or any other metal, that's always the case. That the metal will be partial positive and the hydrogen will be partial negative in this case. Do you follow me? So now typically here, as you can see here, I'm just going to remove this, what we said here. Just going to bring this here. So this is partial positive, this is partial negative. Now, according to Markovnikov rule, generally speaking, the partial part or the electrophilic part should add itself to the carbon with more number of hydrogens, right? While the other part will add itself to the other carbon, and that's exactly what's going to happen. So the first step in this reaction, or the first step in the hydroboration reaction, is following Markovnikov, because simply the boron, which is the electropositive part in this case, adds itself to the carbon. So what we are going to get, but now here, the mechanism, it will be what we call it inserted reaction. We call it it's actually bond breaking and bond making happening at the same time. So in this case, what we are going to get, we are going to get this bonding pairs going here, this going there, and that's what will form here, CH3, CH, then boron, then C, CH3, CH3, then hydrogen. Do you follow me? So as you can see here, you should notice two things, that the boron added itself to the carbon with more number of hydrogens, because simply, it's logic, because simply the boron is the electropositive part here. It's the electrophile in this case. Do you follow me? The other issue here, what you have also to note, that these two will add themselves from the same phase. Do you follow me? In this case, because simply in this reaction here, if you can imagine the transition state of this reaction, you should imagine that the carbon here started to make a bond with the boron. The boron bond with the hydrogen starts to break up. The hydrogen and the carbon starts to make, and this bi-bond starts to break. Can you see? Do you see the green lines here, the green cut lines here? These green cut lines here referring to all bond making and bond breaking happening at the same time. As you can see here, this will never take place unless this bond, the hydrogen boron, add itself from the same phase. That's why what we are going to get, we are going to get this here, this hydrogen and the boron, they should add themselves from the same phase. That's why actually this is what's explaining the selectivity, the stereochemistry of this reaction, which is the syn addition reaction, in which at the end of the day, as you'll see later on, the hydrogen and the OH will be from the same phase. Then finally, it will be after the hydroboration reaction, there will be the removal of the boron bond by simply oxidation of it by addition of H2O2 in presence of OH minus. Simply the OH will displace the boron from the same phase. So what we are going to get finally is CH3, CH, then C, CH3, CH3, and then here we have OH, and then hydrogen. So you should now, or this mechanism should explain to us two things. First thing, at the end of the day, we are getting anti-Markovnikov reaction because simply in the first step, when we had hydroboration reaction, the hydrogen was less electronegative compared to the boron. That's why we got it first from the beginning, from the first step, which is hydroboration reaction. We got the hydrogen in at different carbon, or at the carbon with less number of hydrogens. Then, after we oxidize the boron, we are going to get the OH instead of the boron. And as you can see from the first step, hydrogen and boron added themselves from the same phase. Therefore, we should end up with the hydrogen and the OH at the same phase too. Do you follow me? Is that clear, guys? Is there any question about it, about this reaction, about this anti-Markovnikov addition reaction? All right, so let me just give you an example. At the end of the day, by default, by all means, we must all the time ask you, write down or give the structure of the major organic product showing the stereochemistry. So this is always, keep it in mind, beside any reaction about the mechanism of the reaction. So let me ask you specific question. So give the product of this reaction showing the stereochemistry. In such a type of reaction, you don't need to show the mechanism. For example, this here. write down or give the structure of major organic product showing stereochemistry if needed or if appropriate. I want you to be introduced to this type of reaction of questions, because from now on until the final and in any organic topic, you will always be faced by this question, and you should always be ready to give this information, which is the ability to write down or to complete the reaction and to give the product, the major organic product, and to show stereochemistry of the product if it's appropriate or if it is needed. Do you follow me? So this is always the case. For example, what will be the product if you, for example, allow this reagent or this starting material to react first with pH3 in presence of THF, second with H2O2 in presence of OH minus. Now, to answer this question, I must remember these reagents, what are they used for? As we have explained, this is hydroboration, then oxidation of the hydroboration. This reaction is hydration of alkene in anti-Markovnikov manner, and as well as they are syn addition reaction. So when I want to write a product, I simply have to just write the skeleton as such, because it's just addition reaction, right? So this is the CH3, and the double bond will be removed, of course. What we are going to get, or what we should expect now, that we are going to add hydrogen and OH, but anti-Markovnikov. So there will be hydrogen and OH. First of all, they must be from the same phase, as you can see. This is the stereochemistry. They are from the same phase. Secondly, they are what? The OH here will add itself to this carbon. We have here two carbons before the stereochemistry. It means just the stereochemistry, I will just draw it later on. Now, I will just going to focus on the product. Now, the first thing always, whenever you face any addition reaction, always ask yourself, what are the two carbons of the double bond here? You can see here, we have this carbon, carbon number 1 and carbon number 2. Carbon number 1 is connected to 1 hydrogen, while carbon number 2 is connected to 0 hydrogen. Then, according to this reaction, it's hydration anti-Markovnikov. That means the hydrogen should add itself to the carbon with less number of hydrogen. So it must add here. So this must be the hydrogen, and here must be the OH. Is that clear first? Before moving to the stereochemistry, before showing, because this is not enough yet. If you draw this structure, you will get half of the question. Half of the mark will be, will be deducted. You will lose half of the mark if you didn't show yet the stereochemistry, which we will show it later on. But now, is there any question about the regioselectivity, how these two parts added themselves to the carbon? Any question?
دكتور
Yes, please.
إذا هي أنتاي أو لا يعني أي واحدة يبري.
I'm sorry, I didn't hear you well.
ميز إذا ريدها أنتاي في البداية العادية.
Something wrong with the voice. I really don't understand your question.
كيف نميز إذا يعني
I totally now.
على أساس
Can you write? Maybe it's better to write. Maybe something wrong with the voice from your side. Would you please write down what you want to ask about? Just write down. It's okay, if this is your question, Jawahir, it's part of the knowledge, because from the beginning, when we specified this reaction, we said this reaction is syn addition reaction, and at the same time is anti-Markovnikov reaction. Do you follow me? Was this your question, Jawahir? This is part of your knowledge, because we got this, we have explained this, we have explained it by simply showing you the mechanism. So from the mechanism, we did conclude that two conclusions about this reaction. First conclusion was this reaction is anti-Markovnikov. The second conclusion was this reaction, regarding the stereochemistry, the two adding part must add themselves from the same phase, because it's syn addition reaction. Clear, Jawahir? Perfect. So as you can see here, so from this reaction, from our knowledge from this reaction, we know that this hydration reaction is anti-Markovnikov reaction. That's why we did connect the hydrogen to the carbon with less number of hydrogens, because that's actually the anti-Markovnikov reaction. Now, we must now show the stereochemistry, the correct and the appropriate stereochemistry. We also know about this reaction that these two adding molecule parts, they must add themselves from the same phase, which is simply the meaning of the syn addition reaction. So we must specify that. Now these two parts, the bond here must be, if this is, for example, from the lower side, this OH must also be from the lower side. Do you follow me? Is that clear? Or of course it can be also the opposite. They can be both from the upper side. So which means if this hydrogen is lower side of the carbon, then we must specify that this carbon is simply above the plane. Because very obvious that we must have a tetrahedral at the end of the day for the reaction. Do you follow me? So if you are asked to complete the reaction or to show the product, you must show that product as well as with that stereochemistry. Anything else will be definitely wrong in this case. So you must be very precise and very accurate in giving your answer in this case. So this is always remember this type of question, because we will always ask you about that. Yani, of course, I'm just giving you simply one of the questions which you are going to have in the second exam, in the final exam, and even in the organic 2, and even in organic 3 if you are going to take, or advanced organic chemistry. Always you must be able to get or to draw the structure of the product showing the correct stereochemistry of it. Do you follow me? So these are very important aspects actually of this reaction. Is that clear so far about the hydroboration reaction and this third reaction? Is that clear? Any question about it? All right, let's move to another reaction, which is a hydrogenation reaction. Yes, please.
دكتور ليش دخلنا الهيدروجين والهيدروكسيد اللي هي في السيم سايد مع المفروض مع انتاي ترانس؟
لا هم anti Markovnikov rule. يعني don't mix up things together. Please focus with me. It's a very good question, because we don't just say words. We just simply have to have a meaning in our brain. When we say Markovnikov rule, what's the meaning of Markovnikov rule? Or what's the point of that rule. It's simply specifying to you where these two adding parts, they will connect themselves to the carbons. Do you follow me? The one who asked.
Yes.
So Markovnikov is responsible for determining the position of the two adding parts to the two carbons of the double bond. That's regarding the Markovnikov. So keep it aside now. The other part, which we always must ask ourselves about it, which is the stereochemistry of the adding of these two adding parts. If they add themselves from opposite planes, we call this anti-addition reaction regarding the stereochemistry. If they add themselves from the same phase, the same plane, we call it syn addition reaction. Got it?
Yes, good. Thank
So,
you.
sure, my pleasure. But for everyone else, please, this is very, very important in order not to have any confusion about it. Because these two knowledge are separate. So you always must ask yourself, is this reaction which I'm dealing about, first of all, is it Markovnikov or anti-Markovnikov? As soon as you find the answer, then the second question in your brain must be, what will be the stereochemistry of these two adding parts? Are they syn addition or anti-addition? That's of course from the knowledge of each reaction separately, because we simply study each reaction separately and we explain the mechanism of each reaction.
طيب دكتور.
Yes, please.
كيف نقدر نفرق بينهم يعني بمرة يعني ما صعب الأمور، ما في شيء هندسي يعني يعطيك إنه خلاص نفرق بينهم بمرة؟
والله يعني ما في شيء سحري، يعني ما في شيء انه مجرد انه يعني easy going خلاص شيء ينفع للجميع وخلاص. يعني each reaction we must study it because it's what's determining the outcome. It's simply the mechanism itself. So each reaction has its own mechanism. So that's why actually we need to study the mechanism in order to know what would be the outcome of the product. Unfortunately, والله there is no magic answer for all of these for these questions, except that simply we must study each reaction separately and we must understand the mechanism of each reaction separately. Got it? لكن هو بشكل عام there is something common between all of these reactions. As I said from the beginning or from the previous lecture, if you remember, what we said, the common thing about all these reactions, it's simply that the first step always is the formation of the carbocation. And the most common thing about all of these reactions, that regardless of what reaction we are talking about, always the carbocation which will be formed is the one which is more stable, because that's simply the logic. Do you follow me? So the difference between a reaction and another, it's simply what's the reagent which lead to the formation of the carbocation. Then the second step will be always the addition of the nucleophile. Is that clear?
Yes.
Sure. All right, so the fourth reaction, and then we'll stop. Now, and after that, the lecture today, inshallah, at 2 o'clock, we will continue the reactions of this chapter, because we are actually away from finishing the topic. So we need some time actually to do it. So after we finish the next section, which is the hydrogenation, I'll stop, and then we will continue, inshallah, at 2:15 today in the lab time. No. So the fourth reaction, which we are going to discuss now, it is hydrogenation reaction. Now again, remember, hydrogenation, whenever you hear Asian at the end of the word, what does that mean? When we say Asian at the end of the reaction, what does that mean? Asian refers to what? Addition. Exactly, Ahmed. It refers to addition. Absolutely. Now here, From its name, it's hydrogen. So it is simply, this reaction is simple reaction because it's the addition of hydrogen atoms to the carbon double bond carbon. So whenever we have carbon double bond carbon, now remember, when we want Markovnikov rule, we want to specify if this reaction, when we need to specify if my reaction is Markovnikov or anti-Markovnikov rule. When I need to ask myself, is this reaction Markovnikov or anti-Markovnikov? Or do I need to ask myself all the time? What do you think? Is there a situation where I don't need to ask myself, or I shouldn't bother myself if the reaction is Markovnikov or anti-Markovnikov? Is there any situation?
Maybe if we add just hydrogen.
That's correct. Actually, if we add what we call it, when the general rule here is like that, we should ask ourselves if it's Markovnikov or anti-Markovnikov in one of the two cases. If we are adding, or in one case actually, if we are adding unsymmetrical reagents to, or adding reagents to unsymmetrical alkene. Let me just write it. If we are talking about unsymmetrical alkene reacting with unsymmetrical adding molecules, addition, or adding molecules or parts, let's say. Do you follow me? When we have this, if we have unsymmetrical alkene and we want to react it with unsymmetrical adding parts, then in this case we need to ask ourselves, will this reaction proceed via Markovnikov or will it be anti-Markovnikov? Is that clear? For example, if you have, for example, C the bond C, and here you have R, R, here you have hydrogen, hydrogen. What we classify this alkene? Is it symmetrical or unsymmetrical? Is this alkene symmetrical or unsymmetrical?
Unsymmetrical.
Yes, because simply as you can see, around carbon double bond carbon, this carbon is connected to two carbons while this carbon is connected to hydrogen. If they are connected to the same number of carbons or hydrogens, then we call them symmetrical. So if we allow this unsymmetrical with, for example, AB, adding reagent, if we are allowing it to react with AB, so the adding molecules are A and B, do we need Markovnikov rule here to consider it or to use it in consideration or not? Here.
We
need, because simply this is unsymmetrical reagent reacting with unsymmetrical alkene. So Markovnikov rule or anti must be there. Like if you allow this to react with AA, for example, do you need Markovnikov rule? Or do you need to bother yourself if this reaction is Markovnikov or anti-Markovnikov?
No.
No, not. Because simply it doesn't matter where the A should be attached to. This A or this carbon or that carbon. Because it's the same A. So here there is no Markovnikov or anti-Markovnikov. Do you follow me? Of course, if you have symmetrical alkene, خلاص, by all means, if you have, for example, RR, RR. Here, regardless of what you are reacting, if it is AB or AA, both cases, there is no need for Markovnikov. Because at the end of the day, it is symmetrical, so it doesn't matter where to get what would be by both possibilities, you will get the same product. Do you follow me? So the only way we need to consider, or the only possibility, or the only possibility actually, we must take into consideration the Markovnikov or anti-Markovnikov when we allow unsymmetrical alkene to react with unsymmetrical adding molecules. In this case, we need to know where the A should attach itself. Should it attach itself to this carbon or that carbon? And thus, once we decide for the A, then the B definitely will be the other carbon. I hope this is very clear regarding to the whole issue of Markovnikov and anti-Markovnikov, and when we need to better ourselves to ask a question about it. Is that clear, guys, about the Markovnikov and when we must show the Markovnikov rule?
Yes, Doctor.
Sure. So let's get back to our reaction, or the last reaction, what we are going to discuss today, which is the hydrogenation reaction. And from the hydrogenation reaction, as I said, it's very simple because there is no, especially here, there is no Markovnikov or anti-Markovnikov. Simply, it's the same, it is symmetrical alkene, symmetrical adding reagents. So, with hydrogen. Now, the most important thing, always we need metal here. We need a metal as a catalyst reaction. Do you follow me? Sometimes we may use palladium, we may use platinum, we may use palladium oxide, for example, or platinum oxide, whatever. So we have different reagents actually which can be used for the hydrogenation reaction. I think they are there, for example, platinum oxide, okay, platinum, maybe platinum instead of palladium. But it can be also any metal. Generally speaking, there are plenty of metals which can work. What we are going to get, addition of hydrogens to the two carbons. In this case, we are going to saturate the alkene, or we are going to convert alkene into alkane in this case. Do you follow me? So, regarding this reaction, so the Markovnikov or anti-Markovnikov is out of question. So the only thing we should ask ourselves, what about the stereochemistry of this adding two molecules? Are they, or adding two parts? Are they going to add themselves from the same phase? In this case, we are talking about syn. Or are they going to add themselves from opposite phases? In this case, we are talking about anti. In this case, we have syn addition reaction. Remember that it is syn addition reaction. In other words, the two hydrogens here are adding themselves from the same phase. There is no really, there isn't a real mechanism to show you. What I'm going to show you, it's like this actually. Just going to show you. All right. So it's described in the slide in your PowerPoint presentation. Just going to show you, just to make you understand it easier way. So, for example, in this case, how it will work, how the reaction will work. Actually, imagine that, for example, my hand, it's simply my hand is simply the catalyst, the surface of the metal. Do you follow me? What's going to happen here? Now, what's going to happen is simply the here, as you can see it. Let me just show you here. Now, the first thing here, the hydrogen in this case, what's going to happen, there will be some sort of absorption where the metal here, which is my surface, my hand, they will absorb hydrogen molecule as such. The absorption simply, it will be just like holding the hydrogen molecule as such. Do you follow me? What's then going to happen, this is the alkene, flying alkene, comes and simply react with the two hydrogens and then go. Do you follow me? And then the next alkene comes and then react with the two hydrogens and go. As you can see, the most important thing about all of this, it's simply that the two hydrogens will connect themselves to the alkene from the same phase. That's why we call it syn addition reaction. Do you follow me? In other words, I may just explain it in here, but you can see in here that the hydrogen, this is the surface of alkene, this is the catalyst surface. So this is hydrogen and hydrogen bond. Do you follow me? There will be, it's not a chemical bond, it's like a physical bond with the surface of the catalyst, where we have, I will just relate it to this by this green line here. It's like this is a physical bond, what we call it, so just some sort of adsorption. Then the alkene here will comes, as you can see now, the hydrogen starts to make with this carbon, and this bond starts to break up. This carbon starts to make a hydrogen, a bond with a hydrogen, and this bond starts to break up, and then finally we ending up with the two hydrogens adding themselves from the same phase. Do you follow me? So that's why actually we call this reaction syn addition reaction. It's some sort of saturation reaction actually in this case. Is that clear, guys? Is there any question about this reaction? Any question? All right. We just answer with you the example in the slides, what you have it in the slides. Now imagine we want to just simply specify what's the product of this reaction. So give the product or draw the structure of the product of this reaction. All right. What do you think the structure of the product of this reaction? When this alkene react with hydrogen in the presence of, for example, platinum oxide or platinum oxide, all right, platinum oxide, for example. So what would be, or palladium over carbon? Let me just, I'm just using different ones in order for you to get used to different aspects of the catalyst, what we use. So what will be the product of the reaction? Now, we know that this reaction is hydrogenation. In other words, the two hydrogens will add themselves to the two carbons, first. Second, we know that this type or this stereochemistry of this hydrogenation reaction is syn addition reaction. In other words, the two hydrogens should add themselves from the same plane or the same phase. But the question is, what about the whole stereochemistry? Will it be from, will these two hydrogens add themselves from below the plane or above the plane? Keep in mind that the plane here, which we are talking about, this and the carbon are in the same plane here. So in other words, this is the carbon, the methyl is like this, and my hand is the carbon double bond carbon. The question is like this. Will the two hydrogens comes from below the plane or will they come from above the plane? What do you think? Will they come from, or will they attack from below the plane or above the plane, and why? Will they attack from the top side or from the below side, and why?
Maybe below.
Why?
To avoid repulsion.
To avoid what?
Repulsion.
With what?
With the 2CH3.
Absolutely, thank you very much. Exactly, that's the case, because as you can see, if that's not the case, it doesn't matter. There will be two possibilities. So simply we will have like two products, this or that, doesn't matter. Like if we, because of this here, groups here, they are bulk groups, they will simply avoid, or it will be preferred that the two hydrogens will come from below rather than the attacking from the above the plane. And therefore, actually, the only product what we are going to get for this reaction will be simply, oops, no, it's, yeah, it's fine. So if they're coming from below, that means the hydrogens will be here. That means this methyl must be above the plane. So this will be the major product. Because as you can see here, the two hydrogen will prefer definitely the less repulsive possibility. In this case here, we have that the below the plane, or attacking from the below the plane, will be less repulsion compared to attacking from above the plane. Is that clear, guys? Is there any questions so far about this reaction specifically before we finish up our lecture?
دكتور
Yes, please.
CH3 ليش راحت فوق؟ اللي كانت في الكربون اللي تحت.
صح كلامك. هلا ما بدك تاخذ بعين الاعتبار، يعني just think about it. Here, now here, what's the hybridization of this carbon? What's the hybridization of this carbon? sp2. So what's the geometry around the sp2? What's the geometry? What we call the shape around the sp2? Triangular planar, right? Isn't it?
Yes.
يعني in other words, it's not like, يعني you may imagine it in different, in wrong way. It's actually like this, يعني. In this case, maybe it's not clear. All right. In this case here, as you can see, like this here, you can see, this is exactly the structure. Yani, around this carbon, you will see it's 3 bonds like this. In other words, this is planar. Yani, imagine it like this here, in the same plane. Now we will have, when addition occurs, we are converting from sp2 into what? What's the hybridization around these two carbons? Around any of the two carbons. What's the hybridization?
sp3.
sp3. But now think, now what's going to happen, that we are converting the geometry around the two carbons from planar system like this into three-dimensional structure like this, اللي هو tetrahedral. Do you follow me? This is simply what's going to happen now. Now, therefore now, if, for example here, this was like this here, in other words, think about it like this. This was planar like that. You can follow me. And now the hydrogen, for example here, think about the methyl is the blue one. Do you follow me? Now, when the the black one, I'm sorry. The hydrogen is this one. When the hydrogen, this was planar like that. Do you follow me? When the hydrogen attack from below, this will go above. Do you follow me? And vice versa is true. I mean, if this will attack from here, this will go down. That's exactly what's happened here. This was not below. It's not below actually. It's in the same plane, but this is the way we draw it. It's the same plane like this carbons. Do you follow me? Now, when the hydrogen comes from below, then definitely, if this is below, then definitely this is up. If this is up, then if the hydrogen comes from above the plane, the other carbon must be below. Did I answer your question? The one who asked?
Yes, doctor.
All right, perfect. Is there any other question, guys, before we finish up this lecture? Is there any other question? All right, then I will assume that there is no question. Thank you for attending the lecture. Inshallah, I'll see you in approximately around 2 hours from now. So around, no, 3 hours from now, right? 3 hours? Yeah, around 3 hours from now. So we will meet each other around at 2:15 in the lab time in order to finish up this chapter. Thank you and see you inshallah. Thank you. Assalamu alaikum.